In 2023, the U.S. Defense Advanced Research Projects Agency conducted exercises simulating air combat. The pilot, known as EF-16, with extensive combat experience, fought with artificial intelligence. Following the results of several fights, the score was 5 victories in favor of the artificial intelligence and 0 for the pilot. Why did this happen? Does this mean the end of an era for pilots? Let's start with the areas in which a machine is superior to a person. The first reason is the speed of reaction. A person reacts to a visual stimulus in about 200 milliseconds, while artificial intelligence systems respond in a few milliseconds. In dogfights, this opens up enormous tactical leverage. The second reason is resistance to overloads. The algorithm does not lose consciousness at 9G, and can perform maneuvers that are physically inaccessible to the pilot. The third reason is information processing. The pilot simultaneously monitors the instruments, the horizon, the target and threats from behind, while controlling the aircraft. This is the limit of human attention. The algorithm processes all data streams simultaneously, without degradation. However, machines also have serious limitations. Exercises in a simulator do not reflect a real combat situation. In the simulator, all the data is perfect, there is no interference, no fog of war, no unexpected equipment failure, no enemy with non-standard tactics that are not in the training set. A person knows how to improvise, make a decision in a situation that has never happened. The algorithm operates within the framework of what it has been trained to do, and may be powerless in the face of an unforeseen circumstance. That is why the concept of the 6th generation of aviation is not focused on a completely unmanned fighter, but on the joint work of a pilot and a swarm of unmanned vehicles. A person is responsible for strategic decisions, a machine executes them quickly, accurately, and without fear. This is a partnership, not a replacement. In narrow air combat missions, the vehicle is already showing better results, and it is difficult to accept this fact, but it is pointless to deny it. The future of military aviation is not about making the pilot better, but about placing him where human intelligence is indispensable, and removing him from where he is the weakest link. Military aviation is a constant dialogue between the possible and the impossible. Every decade, what seemed like science fiction becomes standard equipment: guided bombs, invisible planes, missiles that travel 20 times faster than sound, machines that win dogfights against humans. Behind every technology there are people, engineers who solve problems at the edge of the possible, pilots who trust their lives to these decisions, technicians who keep everything in working order. The sky does not forgive mistakes, so technology development in this area is happening faster than in any other area. This is why today we see accelerated growth in hypersonics programs, improved communications systems, and increased interest in integrating artificial intelligence into controlled aircraft. The transition from experimentation to practical use is expected in the coming years, and this transition will determine the balance of power in air operations. In the modern combat aviation world, every element of the aircraft and every flight preparation process becomes the object of constant engineering testing. Over the past few decades, the armed forces of the largest maritime powers have undergone a radical transition from traditional steam catapults to electromagnetic ones. This transition has become one of the central topics of recent news in the field of naval aviation. This review looks at how the way aircraft can be accelerated from the deck has changed, what new demands are placed on pilots, and what technological solutions can overcome the limitations of older systems. At the beginning of the 21st century, a steam catapult was used on board most American aircraft carriers, known under the symbol C-13. The principle of its operation was simple. High-pressure steam pushed a piston along a long cylinder, and a special connecting rod mechanism captured the plane and accelerated it. In 2 seconds, the piston reached a speed of 270 km per hour, and the load felt by the pilot was approximately 3G. At first glance, such a system looked reliable, but its operation required enormous amounts of energy. Steam generators constantly produced steam between starts, and the minimum interval between starts was limited to 20 seconds. During intensive operations this became a bottleneck. Accurately adjusting the steam system pressure was critical. If the steam was not strong enough, the plane could not reach the required speed and fell into the water. If there was an excess of steam, it created excessive overload, which could lead to damage to the airframe. In addition, each aircraft had its own mass, and each launch required individual calculations. Such nuances made the steam catapult one of the most complex mechanisms on the ship. All these limitations motivated the development of new technology. On the aircraft carrier Gerald Ford, the first electromagnetic catapult, designated EMOLS, replaced the steam system. Instead of a piston, a linear electric motor was used, reminiscent of the operating principle of magnetic trains, but instead of a carriage, a heavy combat aircraft was accelerated. The electric motor accelerated the aircraft along a pre-programmed curve, which avoided a sharp impact and extended the life of the airframe. The energy required for a single launch reached 100 megajoules, which is comparable to the energy consumption of a small plant for several minutes. This energy was stored in large rotating flywheels and released within seconds at the moment of launch. Theoretically, an electromagnetic catapult could launch aircraft of any weight, from a heavy attack aircraft to a light unmanned aerial vehicle. The steam system had minimum weight restrictions, and lightweight drones were often destroyed when attempting to launch. However, in the first years of operation, EMOLS showed a number of problems. The control system failed, and instability was observed at high launch rates. The U.S. Navy has spent years refining the software and improving the electromagnetic components. Today, the electromagnetic catapult is considered reliable, but its implementation remains an example of how new technologies can turn out to be more expensive and more complex than originally thought. In addition to acceleration issues, pilots face the physical limitations of their own bodies. When accelerating at 9 gs, the weight of the body increases 9 times. If the pilot's weight was 80 kilograms, then under such a load he would feel a weight of 720 kilograms. A heart accustomed to normal blood circulation would have to overcome 9 times the force. Blood moved to the lower body, legs and abdomen, and the brain received less oxygen. With an overload of 5G without protection, the pilot lost consciousness within 3 to 5 seconds. This phenomenon was called J-lock, and in combat conditions, loss of consciousness even for a few seconds could be fatal. To combat this effect, military aviation uses an anti-cargo suit known as a G-suit. The principle of its operation is simple. The suit is worn over flight equipment, covers the stomach, thighs and legs, and there are special cameras inside. When the load exceeds 2G, the sensor activates the compressor, which instantly fills the chambers with air. The suit compresses, trapping blood in the upper body, thereby maintaining oxygen flow to the brain. Modern models are capable of increasing the tolerable overload by about 1.5 to 2 gs compared to an unprotected person. New generations of anti-cargo suits installed on modern combat aircraft include the ATAG Advanced Technology Anti-G Suit System. This system covers the entire body from the ankles to the shoulders and includes a special vest that compresses the chest, making breathing easier during high loads. Pilots are taught a special breathing technique, the anti-G maneuver, in which tensing the abdominal muscles and taking a special breath increases the pressure in the chest. This technique requires months of preparation, and an incorrectly performed maneuver can lead to premature loss of consciousness. For American fighters, the official overload limit remains 9G. Exceeding this limit creates the risk of compression injuries to the spine. Statistically, modern fifth-generation pilots suffer from neck and back problems more often than their predecessors. The human body remains the most vulnerable element in complex aircraft, and there is no technology yet that can completely eliminate these limitations. Let's move on to another critically important topic, missile navigation. When a pilot fires a missile, the target is tens of kilometers away, with air masses, clouds, and potential interference flying between them. There are several fundamentally different guidance methods, each of which represents a separate engineering challenge. The first method is infrared guidance. The missile sensor detects the heat signature of the target's engine. The classic Sidewinder and AIM-9 family rockets used exactly this technology. They effectively hit targets at short distances, up to 35 kilometers. However, opponents began to use heat traps, squibs that burned brighter than the engine, misleading the missile. Modern infrared homing heads have become more intelligent. They analyze the shape of the heat spot, its movement and spectral composition, which makes the task of decoys more difficult. The second method is radar guidance. The missile is equipped with its own radar, which independently searches for the target. After launch, the pilot can deviate from the trajectory, and the rocket continues to operate autonomously. An example of such technology is the AIM-120 missile, known in Russia as AMRAAM, capable of hitting targets at a distance of up to 180 kilometers in modern modifications. The main problem is the possibility of creating radar interference from the target. In response to this, developers are constantly improving interference suppression algorithms, but the technology race continues. The third method is combined. At the initial stage, the rocket follows an inertial trajectory obtained from preliminary calculations. Then ground or airborne radars correct its course through radio channels. At the last stage, the missile's active radar turns on and locks onto the target. This approach is used in most modern long-range missiles, allowing for a combination of accuracy and flexibility. New multispectral seekers combine infrared and radar sensors. It has become almost impossible to deceive them at the same time. It is necessary to simultaneously create a thermal trap and radar interference. Signal processing algorithms continue to develop, making rockets more and more smart. Rocket flight is not just throwing a projectile, but the flight of an autonomous computer that makes decisions faster than the pilot. This idea underscores the importance of developing and testing new guidance systems. An important aspect of the operation of combat aircraft is the sound factor. When flying an afterburner, a jet engine creates a loud noise, reaching about 140 decibels at low altitude. For comparison, the human pain threshold is about 120 decibels, and the afterburner exceeds it. This noise is caused by turbulence, which occurs when there is a sharp difference in the speed of the exhaust gases and the surrounding air. In civil aviation, dual-spool engines are used, where a large fan in front of the core reduces the speed difference and reduces noise. Military fighters seeking maximum thrust in a minimum size use engines with low bypass ratios, which results in louder sound. When the afterburner is turned on, additional fuel is added to the engine, which burns in the chamber after the turbine, increasing thrust by 60 to 80%. The exhaust temperature exceeds 1,600 degrees Celsius, and the gas speed becomes enormous. The result is a sharp increase in acoustic load. For this reason, military airfields are located away from residential areas, and personnel wear air protection that reduces noise levels by more than 30 decibels, otherwise hearing loss becomes almost inevitable. Engineers continue to look for ways to reduce noise. Special nozzle profiles are being developed to allow the exhaust gases to mix more smoothly with the surrounding air. However, in combat aviation, the priority remains maximum thrust, not environmental friendliness, so it is not yet possible to completely get rid of noise. Precision navigation and bomb control have also undergone a revolution. During the Vietnam War, the U.S. Air Force dropped hundreds of conventional bombs, but their accuracy left much to be desired. Later, laser-guided bombs were used in Iraq, but their effectiveness depended on the presence of a laser designator, which could not operate in cloudy weather. The JDAM, Joint Direct Attack Munition, system changed the approach, making it possible to turn a conventional unguided bomb into a precision weapon. Inside the block, attached to the bomb body, there was a GPS receiver, an inertial navigator and aerodynamic rudders. After entering the coordinates of the target, the bomb itself adjusted its flight, achieving an accuracy of about 10 meters, regardless of weather conditions. The cost of the JDAM kit was about $20,000, which was significantly cheaper compared to expensive laser ammunition that required a separate laser carrier aircraft. Later, JDAM modifications with drop-down wings appeared, increasing the planned range to 75 kilometers, allowing the bomb to be released from a safe zone inaccessible to air defense. The small version, known as the GBU-39, had a diameter of about 170 millimeters, and one fighter could carry up to 24 such ammunition. This opened up the possibility of delivering several targeted strikes on different targets simultaneously, replacing one large explosion with many small but accurate ones. The accuracy of such ammunition not only changed tactics, but also influenced the ethics of the use of force. When hitting a target with an accuracy of 10 meters, destruction around is minimized, although the war remains a conflict. However, from an engineering point of view, such technologies make combat operations fundamentally different. Aerial refueling represents another key element of modern strategy. When flying at a speed of 500 km per hour at an altitude of 7 to 8,000 meters, two aircraft can be 15 meters apart. The tanker operator, controlling an 11-meter-long boom, is connected to a receiver on the fuselage of the fighter. After connection, the fuel begins to flow at a speed of about 1,400 liters per minute. The US Navy system uses a rigid rod controlled by a joystick, while European and British variants use a flexible hose with a funnel, known as a probe and friend. In the latter case, the pilot himself directs the probe into the funnel, which simplifies the tanker's work, allowing one tanker to serve several aircraft at once. Why is aerial refueling needed? Without it, a fighter can only fly about 1,500 kilometers, while with refueling the range expands almost without restrictions, as long as there is enough crew and fuel. In 1998, American F-11 model fighters flew from the United States to Libya, covering a distance of about 13,000 kilometers, refueling in the air several times in both directions. This opportunity made the global presence of American aviation a reality. Tankers such as the KS-135 and KS-10 became the invisible heroes of every operation, providing range without the need for land bases. The concept of a tilt-rotor, capable of taking off like a helicopter and flying like an airplane, also attracted the attention of engineers. The idea was to use a tilt-rotor, two large propellers at the ends of the wings, which rotate vertically during takeoff and horizontally during flight, turning into ordinary propellers. However, a transient regime known as a vortex ring presented a serious problem. During a rapid vertical descent, the rotor would become caught in its own downdraft, losing lift and causing an accelerated fall. Helicopters can exit this mode by accelerating forward, but with a tilt-rotor this happened faster, and rescue was more difficult. In 2001, the tilt-rotor V-22 accident killed 19 people, and the project was in danger of being closed. Subsequently, flight restrictions and training programs were changed. The pilots were trained. Plasma cocoon. During hypersonic flight, a shell of ionized gas plasma is formed around the aircraft. Plasma absorbs radio waves. The device disappears from radar, but at the same time loses contact with ground control. How to transmit course correction commands through the plasma cocoon? This task remains open. Different countries are looking for solutions, special antennas, laser communications, pre-programmed maneuvering algorithms. The US is responding with several parallel projects. The HLLK program, High-Speed Attack Land and Launch Crews, Argus Reconnaissance Hypersonic, as well as the operational program for the LHV Army Long-Range Hypersonic Weapon. Hypersound will not change the war tomorrow, but in the near future it can change everything. The bottom line is that hypersonic technology is a game changer, but it will not replace the human factor. Instead of replacement, they create a new form of interaction where man and machine act as a single brain. This synthesis promises a more flexible and effective combat structure, capable of adapting to unpredictable conditions. In this context, the future of military aviation looks like a joint flight between the pilot and the intelligence swarm, where each side enhances the capabilities of the other, and the common goal is to ensure air superiority.